Hello, I want to talk to you about two cycloaddition reactions that are new to us. A ketene 2+2 cycloaddition, which is a thermal 2+2, which is unusual. And I want to talk to you about the ene reaction, which is a reaction we haven't met yet, similar to the Diels-Alder reaction, but different in a fundamental way. So let's start by talking about ketene 2+2 cycloadditions. So here's an example of a ketene reaction. So we start with what looks like a great Diels-Alder diene, react it with this acid chloride in base, and then we end up with this four-membered ring. Clearly not the product of a Diels-Alder reaction. So what's going on in this reaction? So what's going to happen is that we're first going to have the base do an elimination. So the base is going to deprotonate, and we're going to do an E2 reaction to generate the ketene. All right, and so that's going to give us dichloroketene. And again, remember the way that ketenes are drawn with the dot here, that dot is just a carbon, right? So nothing crazy going on, it's not a radical, it's just a carbon. So now you have your ketene, and again, it's important to think about why can ketenes undergo thermal 2+2 reactions, because those are reactions we said don't happen. Thermally, we're supposed to get a 4+2 or Diels-Alder type process. So that's something I want you to think about. We'll talk about in class. Why do ketenes do that? The ketene is then going to react with the ketenophile. And so we're going to get a 2+2 cycloaddition, and that will give us the product drawn over here. Right, so it's an E2 reaction to form the ketene, highly reactive species, often you generate it in situ, then it reacts with the ketenophile. It's also important to recognize that we do not get the regioisomer, right? So this is the product, and that's not formed, or it's formed as a minor product, right? And so I want you to think about how to explain that regiochemistry. I think that's an important point, and we can talk about that in class. All right, and then another example of a ketene reaction is down here where we would do this intramolecularly. Right, so relatively complicated molecule. We're going to do the exact same initial reaction to form the ketene. So we would get that ketene. And so the question is, what product do we get from this thing doing an intramolecular ketene reaction? So take a minute, see what you would do for this. And let me draw out, there are two possible products, so let me draw them out. And then you can see if you can figure out what's going on. So our two possible products are the following. And that's generally the product that most people draw. And it turns out that that does not form. And that the product that we get is a very interesting structure. That looks like that, right? That's our product. So my question to you is to explain why this doesn't form and why that is the product for this intramolecular ketene reaction. All right, so let's turn our attention to the ene reaction. Right, so we'll move on from the ketenes. And let's look at the ene reaction. All right, this is formally a 4+2 cycloaddition. And let me just give you an example of an ene reaction. So we have our ene and our enophile, and we will end up with that as the product, right? So it doesn't look like a pericyclic reaction. It doesn't form a ring. So this is definitely an odd reaction for us, right? So what's happening here? So let's look at the mechanism for this reaction. And the interesting thing about this reaction is that instead of having all pi bonds involved, we have a CH sigma bond involved in the reaction, right? So we're going to have those bonds forming, right? And so this is going to be our pericyclic process, where there are the 4 electrons that are moving, 2 from pi bonds, 1 from a sigma bond. And when we do that, we end up forming the product over there. Right, so a very interesting cycloaddition reaction with a sigma bond. Right, so let's look at a couple of examples. Right, so this is an example of an intermolecular reaction. These are relatively common. So this is what we would say is the enophile. Right, another example that looks just like this. So put this into our intermolecular reaction. So this will be example number 1. And we can just do example number 2 over here. And it's pretty common to do these things with maleic anhydride. So that's a good enophile. And again, often you have some sort of Lewis acid to promote the process. But again, here it would look like this. Right, and so then you can just draw out the product that you would get. Right, and so that would be your product from that intermolecular ene reaction. Right, intramolecular is definitely more common. So let's give that number 1. Intramolecular are more common, so we will see more often these things happening intramolecularly, right? So what's an example of an intramolecular ene reaction? So if you heat this up, there are actually 2 ene products that you can get. You can get the spirofused 5,6 system, and then you can get a 5,7 system. Right, those are the 2 possible ene products, and this one is the product, and this one is not formed. Right, so that's another question that I want you to think about when you're thinking about the ene reaction, is why do we form this product? And why do we not form that one? And what mechanisms would enable us to account for what's going on here? So I want you to think about that one. And then the most common type of ene is called a carbonyl ene reaction. And an example of the carbonyl ene is where a carbonyl is the enophile, right? And so here's an example of a carbonyl ene reaction. So if we have this as our ene, and then we add formaldehyde. All right, what happens when we do this reaction? And again, Lewis acid is a common promoter for this, so we're going to form that bond, and then we're going to form an OH bond. All right, so you can imagine the electrons flowing like that. And what do we end up with? We end up with, and if you draw it out, again, make sure you're breaking and forming the right bonds, you end up with a double bond over here, right? And then an alcohol, right? And this is a homoallylic alcohol, right? Product equals homoallylic alcohol, right? And in this case, homo just means an extra carbon in between the alcohol and the alkene, right? So not an allylic alcohol, but a homoallylic alcohol. And this is the retron for the carbonyl ene. Right? It's not always easy to spot the use of a regular ene reaction just looking at the products, but a carbonyl ene, it is relatively easy to spot because it's this homoallylic alcohol. So that's something that we should definitely remember. Right? So in closing, ketene cycloadditions, we should really think about how they're possible, because thermal 2+2 cycloadditions generally don't happen, but they do with ketene. And the ene reaction, we should just practice this cycloaddition that involves a sigma bond in addition to 2 pi bonds. And we'll practice these with the problems that you're working on.